I wanted to deliver a single lecture titled, Does the Perturbation Series in Quantum Mechanics Converge? But in an attempt to provide the necessary background, that lecture got way too long, so I split it into two parts. This is part 2. In part 1, we essentially reviewed the topic of asymptotics, which is extremely important as a technical topic for mathematical physics and engineering. However, it's hardly ever taught in most of the beginning courses as part of mathematical physics, so I had to give a quick review and rather scanty review of the topics covered there. We essentially talked about two functions f of x and g of x being asymptotic at x goes to x0, denoted by this: if the difference fx minus gx is negligible compared to gx as x goes to x0. Negligible here simply means that the ratio of fx minus gx over gx in the limit x goes to x0 must vanish, and therefore fx and gx being asymptotic essentially can also be written down in this form: limit as x goes to x0 of fx by gx, this ratio, is 1. So if two functions are asymptotic to each other as x goes to x0, they essentially are very close to each other in the sense of ratio. Now, the more important version of asymptotics that we needed was the concept of an asymptotic series, where fx, a function, is considered to be asymptotic to a series of powers of x minus x0, sum over n running from 0 to infinity of an x minus x0 to the power n as x approaches x0, if for each and every capital N, the difference between fx and the partial sum up to capital N is negligible compared to x minus x0 to the power n. We discussed this in the last lecture in some detail, and we showed that if yx has derivatives of all order at x equal to x0, then its asymptotic series as x goes to x0 exists, is unique, and it matches the Taylor series irrespective of whether the Taylor series converges or not. If the Taylor series converges, it happens to be the same as the asymptotic series. Even if the Taylor series does not converge, the asymptotic series is still exactly made out of the same terms. And we worked out a particular example in some detail. I am just quickly telling you what we found out there simply because we are going to use essentially the same techniques in today's lecture involving the actual perturbation theory in quantum mechanics. We talked about a particular second order differential equation x square y double prime plus 1 plus 3x y prime plus y equals 0, for which x equal to 0 is an irregular singular point. We found out that there is a power series kind of solution for y of x if you leave out this overall constant y0. The rest of this is what is called the Stieltjes sum, and it's rather easy to check that this series actually has a radius of convergence of 0. But we first showed this using the power series method. By using the power series method in the differential equation, we arrived at this solution. Then we realized that because the power series does not converge, some of the mathematical steps there may have been mathematically a bit illegitimate. We then recovered this series by directly calculating the derivatives to all orders of y which satisfies this particular equation. And we also saw that for small x, the Stieltjes series, this divergent series, is actually quite useful for evaluation of this entity. Now, with this background, we are going to talk about today's main topic, the main topic of this series of lectures. It was meant to be one lecture but has turned out into a two-part series. on perturbation theory in quantum mechanics. So going back to perturbation theory, this is what we are trying to solve for. You have a Hamiltonian which is the sum of an exact Hamiltonian H0 plus a perturbation term H0 plus lambda H prime. So this is a function of lambda, the Hamiltonian. Its eigenkets and eigenvalues are also functions of lambda. Now what we do is we expand epsilon I lambda in a power series, at least a formal power series in lambda. We say formal simply because at this stage we have no guarantee that this series is going to converge. And then, not only that, we also expand the psi I lambda, the ith energy eigenfunction, in a power series with lambda as the parameter. And of course, each of the coefficients here are actually kets. Now, it's easy to see that here the epsilon I comma m, each coefficient, the coefficient of lambda to the m in the expansion of epsilon I lambda, the ith energy eigenvalue of this h of lambda, are nothing but Taylor series coefficients of epsilon I lambda. So if you differentiate epsilon I of lambda m times with respect to lambda, divide by m factorial, and of course evaluate it at lambda equal to 0, you are going to get these coefficients. The psi i's lambda's expansion involves kets. To make this simpler, what we do is we use the complete set of eigenkets provided by the exactly solvable Hamiltonian H0. H0 has eigenkets phi 1, phi 2, phi 3 and so on. A general eigenket is phi n, whose energy eigenvalue we are denoting by epsilon n0. The 0 here tells us that we are talking about the eigenvalue corresponding to H0. And in terms of the basis provided by the INs, we can expand the mth coefficient in the expansion of psi I. So psi I lambda essentially is psi I 0 plus psi I 1 times lambda plus psi I 2 times lambda square and so on. The coefficient of lambda to the m in that expansion, psi I m, can be written now as, well, the notation is a bit clumsy here, sum over all n. This is a sum really over n. I should actually mention that. Ci comma n's nth coefficient, and of course the basis vector phi n sitting here. Now, by adding up all the contributions coming from phi n to all orders, basically we can also rewrite psi I lambda as sum over all n phi n with coefficients bi lambda's nth coefficient. So here the I simply stands for which particular energy eigenfunction you are talking about. N is the real coefficient here in the sum. And bin lambda is simply a perturbation series with Cim and these coefficients being the coefficients of various powers of lambda. So, in principle, if you differentiated bin lambda m times with respect to lambda, put lambda equal to 0 and divided by m factorial, you would get the coefficient Cim's nth coefficient. These are actually the coefficients which sit in the perturbation series for the wave functions. The trouble is, we use perturbation series by essentially not doing differentiation of this kind, but just plugging in the power series expansions in the equation h lambda psi lambda is epsilon I lambda psi I lambda, and then match term by term, that is match powers of lambda on both sides, and write down a sequence of equations, solve them to find out these coefficients. But if the series for epsilon I lambda and bin lambda do not converge, and more often than not, for interesting cases they do not, can we actually trust the perturbation theory results at all? The whole procedure although we do call it formal, does seem to reek of mathematical, chicanery somehow. We are actually carrying out a term by term expansion by multiplying two series out, and a mathematician would tell you that that actually is a valid thing to do if the series were not only convergent, they were absolutely convergent. Here we would often end up with series which are not even convergent. So what exactly does the perturbation theory results tell us? And are they of any use? That's what we are going to try to answer in today's lecture. Now, this thing has been treated in quite some detail in a paper published in the Journal of Mathematical Physics. This is a pretty old paper, published in March 1968. This is volume 9, number 3, written by J.B. Krieger and called Asymptotic Properties of Perturbation Theory. What we are going to do is we are going to show that the perturbation series actually produces an asymptotic series, and we are going to follow the procedure that we actually adopted for our differential equation in lecture 1. So if you are already familiar with asymptotics, you can dive right into this lecture. If you think you need some background before you get into this, I would suggest either read a decent book on asymptotics, there are plenty of them available, or go and watch part 1 first. Our starting point here will be the basic equations. H lambda psi I lambda is epsilon I lambda psi I lambda. This is just the eigenvalue equation for h of lambda, as we have already mentioned before. And psi I lambda will be expandable in terms of energy eigenfunctions of H0. H0 phi n is of course given by epsilon I n0 phi n, and these phi n's are chosen to be orthonormal. So this is basically our starting point. We will deal directly with these functions xi lambda and bi lambda and try to calculate the derivatives starting from these equations and show basically that you get the same results this way as you would get from the perturbation theory. So we would essentially be doing the same thing that we did with the differential equation in the last lecture. We will be showing by direct differentiation of the fundamental equations that the coefficients you get in the perturbation series are actually the coefficients of the Taylor series. That is, coefficients you get by successive differentiation of the functions involved. Now, in order to do this, we will first change these equations into equations involving these functions directly. For that, we will just start with h lambda being h0 plus lambda h prime, and instead of psi I lambda, I will plug in this expansion in the basis of h0 wave functions. Sum over n prime, bn prime lambda phi n prime. I've just called this dummy index of summation n prime instead of n because we will have to deal with the specific n soon. This is the left hand side. On the right hand side, we have epsilon I lambda, sum over n prime, bn prime lambda phi n prime. Note that if you were doing perturbation theory, you would actually be expanding this out in powers of lambda along with this, and then match term by term. We are not really doing that here. What we are going to do is hit this with a particular bra, the bra corresponding to phi n. This is a specific n, and that is precisely why I wrote n prime here. So when I do that, note that the first term that I get here will be phi n h0 sum over n prime bn prime lambda phi n prime. Since h0 has phi n as an eigenstate, the bra phi n acting on h0 is nothing but h0 phi n's adjoint, corresponding bra that is, and this is epsilon n0 phi n's adjoint, and this is nothing but the bra phi n multiplying epsilon n0's conjugate, but conjugate here is just the same as epsilon n0. Epsilon n0 being the eigenvalue of a Hermitian operator, is real. So when this calculation is done, this just gives you epsilon n0 phi n. Phi n being a bra is a linear functional acting on kets to give numbers. So when it goes and sees the sum, it essentially jumps through the coefficients, hits the phi n prime, and phi n prime, because of the orthonormality, gives me delta n prime, and the sum over n prime becomes trivial. I've just shown this particular calculation in some detail, but it's pretty easy and standard. The first term here, h0 bn prime lambda phi n prime sum over n prime, upon being hit by the bra phi n, gives you simply epsilon n0 bn lambda. For the second term, phi n hitting h prime, that of course gives us a bra, but we do not really know what that is. At least we know what that is if we know h prime, but there's no easy result for that here. Here all that happens is lambda, of course, being a constant, a number, just comes out. Then you have the sum n prime. Phi n prime goes and enters that. Bn prime stays outside the action of phi n prime, simply because phi n prime is linear. And you end up with phi n h prime phi n prime times bn prime. We give this particular matrix element a name. This is a standard name that we give to matrix elements in quantum mechanics. This is called h prime nn prime. And with that abbreviation, you end up with this particular equation. But before we go there, let's look at the right hand side also first. When you hit this with phi n, it's pretty easy. The epsilon I lambda comes out. The sigma over n prime bn prime lambda phi n prime gives you delta n prime. So this just becomes epsilon I lambda bn lambda. So now this equation can be easily rearranged in this form. So this is my basic Schrodinger equation, the eigenvalue equation, rewritten for the functions epsilon I lambda and bn lambda. You may have already noticed one thing. I should have actually mentioned this before. I wrote this expansion as bn lambda. I dropped the I. I had earlier written this just a while ago as bin lambda. I just simplified the notation by just dropping the I and moving the n from a superfix here to a suffix. I am pretty sure that this is not going to lead to any confusion because we are talking about the ith eigenfunction and ith eigenfunction only. So dropping the I should not make for any further confusion. What we end up with is this equation, which is exactly equivalent to the Schrodinger equation, which relates the functions of I lambda and bn lambda to each other. Now, one result which immediately follows from this equation is what we get when we take the limit lambda going to 0. Assuming that this sum stays finite in the limit, the whole right hand side vanishes. So you are left with epsilon I at lambda equal to 0 minus epsilon n0 times bn at 0 is 0. Now this means that either this is 0 or this is 0. So either you're talking about epsilon I lambda 0 being equal to epsilon n0 or bn0 vanishing. In other words, the value of the epsilon I function at the origin, at lambda equal to 0, must be one of the energy eigenvalues. We obviously choose it to be the ith unperturbed eigenvalue for H0. And then Bn0 must vanish unless epsilon n0 matches epsilon I0. So Bn0 must be 1 if n is equal to I and 0 if n is not equal to I. Now here, a slight complication in the notation would arise if you had degeneracy in the ith energy eigenvalue, because then there would be multiple eigenfunctions corresponding to the same eigenvalue, and then Bn0 equal to delta In may or may not be correct. But here we assume that we have actually implemented the degeneracy breaking step in degenerate perturbation theory properly, and that will ensure that delta In is exactly what you get for Bn0. This will actually pick out one energy eigenfunction and only that will have a non-zero coefficient. The others, even if they were degenerate, would have zero coefficient. If you are a bit confused about this, I would urge you to review degenerate perturbation theory and exactly how perturbation lifts the degeneracy in such cases. So basically what we are going to do is we are going to choose the basis phi n in such a way that if epsilon I0 is degenerate, then each of the states that the degeneracy breaks up into, they are going to be chosen as basis vectors for the degenerate subspace. Well, that's a small technical point and it doesn't really have a huge bearing on the rest of our argument. Now, there's one more thing that we are going to use, at least Krieger used it in his paper. Not really essential as you will see, but it does simplify some of the calculations. We are going to actually make use of something called the Feynman-Hellman theorem, which I have talked about before in my treatment of perturbation theory in the advanced quantum mechanics course. But in case you have missed that lecture, let me just briefly review what the Feynman-Hellman theorem is. The Feynman-Hellman theorem essentially deals with a situation where you have a Hamiltonian which depends on some parameter. I'm calling the parameter lambda here, but note that in perturbation theory we have some notion that the parameter should be small in some sense, so that the perturbation expansion actually can be stopped at a small order without having to really calculate infinite number of terms. But as far as the Feynman-Hellman theorem is concerned, there is no need for lambda to be small in any sense. This is just some parameter my Hamiltonian depends on. So h lambda psi lambda is given by energy eigenvalue which depends on lambda, and of course the ket definitely depends on lambda. Now, if I just partially differentiate this entire expression with respect to lambda, I end up with this expression. Now, I'm not sure whether you know how to differentiate an operator acting on a ket, but basically, it essentially boils down to a formula which looks exactly like a differentiation of a product. So you differentiate the Hamiltonian operator that acts on the ket psi lambda, then you keep h lambda intact and partially differentiate the ket psi lambda. On the left hand side, you have a vector times a scalar. The same process works there. E lambda del lambda of psi plus del E lambda del lambda psi lambda. This is what you get if you were to do a partial derivative. Now, what we are going to do is sandwich this with a bra on the right, and the bra that I am going to use is psi lambda. So, this becomes psi lambda del h lambda psi lambda from this term. Psi lambda h lambda del lambda of psi lambda from this term. E lambda, of course, moves out of the psi lambda because it's a function. Psi lambda is a linear operation. And psi lambda del lambda of psi lambda here. Plus del E lambda del lambda, which also moves out, and you have this psi lambda, which of course, if psi is taken to be normalized, is simply 1. Of course, not 0. Now, note that h lambda psi lambda is simply E lambda psi lambda. And therefore, this term and this term exactly cancels each other out. So what we end up with is the Feynman-Hellman theorem. The rate at which the energy eigenvalue changes with the parameter present in the Hamiltonian, del E del lambda is nothing but the expectation value in the lambda eigenket. The eigenket corresponding to lambda. This is the perturbed eigenket if you are doing perturbation theory. But the expectation value of del h lambda del lambda in that. Now, in our case, del h lambda del lambda is simply lambda prime because h lambda is h0, which does not depend on lambda, plus lambda into h prime, where h prime also does not depend on lambda. So this is what my del h lambda del lambda is. Psi lambda has been expanded in h0 eigenstates in this form. And E lambda on this side are nothing but the epsilon I lambdas, the eigenvalues of h lambda that we are talking about. So the Feynman-Hellman theorem for our problem simply becomes partial derivative of epsilon I lambda with respect to lambda has to be, this is the bra psi lambda, the bra corresponding to this, where bn star lambda phi n bra, sum over n. Then you have h prime, which is the del h lambda del lambda sandwiched here, and followed by the ket, where I've just changed the dummy index to something else. And this simplifies very easily to this result. The partial derivative of epsilon I with respect to lambda is given by the sum over both n and n prime of this quantity bn star lambda, bn prime lambda, and phi n h prime phi n prime, the sandwich which is the matrix element h prime and n prime. So we have two basic equations, one of which is just the Schrodinger equation, this one, which is the main equation for us, and the Feynman-Hellman theorem's version here, which simply becomes this. This one has some calculational advantage, although you could have done without it. But let me just show you what kind of advantage you get. One thing that you can calculate immediately from this is the value of del epsilon I lambda del lambda at lambda equal to 0. If you put lambda equal to 0 on the left hand side here, you actually get the first order correction to epsilon I. And what you get on this side is delta In from Bn star lambda, delta In prime from this, h prime and n prime summed over n and n prime. And because of the magic of the delta symbols here, this sum is trivial, it's just h prime II. So this is what I get. Del epsilon I lambda del lambda at lambda equal to 0 is simply h prime II. This is nothing but the first term, the 1th term rather, in the perturbation expansion of epsilon I. And notice that perturbation theory actually does give you exactly the same result. It tells you that the first order correction in the ith energy eigenvalue is given by the matrix element of the perturbation in the ith energy eigenstate. Here, these are unperturbed energy eigenstates where you are taking the matrix. This exactly is perturbation theory to the first order. And note, we could have derived this without doing perturbation theory. All we did was use the Feynman-Hellman theorem. Now, let's see what we can actually deduce from the more important equation, the Schrodinger equation itself, which in our language has taken this particular form. Now, in order to get an important result out of this, what we do is differentiate with respect to lambda. So what we get is del epsilon I lambda del lambda from this factor. Epsilon n0 of course does not depend on lambda. It's a property of the Hamiltonian H0, the exact Hamiltonian, which doesn't have any lambda in it. So derivative is just this much times Bn lambda plus this whole factor into del Bn lambda del lambda. Just ordinary differentiation of products. On the right hand side, if you differentiate this whole thing with respect to lambda, you get this term here plus lambda times the derivative of this with respect to lambda, which is just h prime and n prime del Bn prime del lambda at lambda. This is pretty straightforward. What we do after that is put lambda equal to 0. And this gives us del epsilon I del lambda as lambda goes to 0 times Bn at 0 plus epsilon I at lambda equal to 0 minus epsilon n 0 times del Bn lambda del lambda at lambda equal to 0 is given by this. N prime sum of h prime and n prime Bn prime 0 plus, now this is tricky in the sense that you have to remember that this would have vanished, but we have to be a bit more careful than that. Let's just say it's 0 times the value which this sum has at lambda equal to 0. The reason why we have to be careful is that before we set this equal to 0, we have to make sure that this sum does not diverge. Note that the sum is over all possible states, so it's an infinite sum. So divergence is sometimes on the cards. So just because it's being multiplied by 0, we can't simply ignore this. But let's see. As long as this sum is finite, and we will see what that finiteness means soon, what this gives us is the following. This quantity, del epsilon I del lambda at lambda equal to 0, we have actually worked out that this is h prime I using the Feynman-Hellman theorem just a while ago, times delta In plus epsilon I0 minus epsilon N0. This we have already worked out from the equation directly by putting lambda equal to 0 in the Schrodinger equation directly, that this has to be epsilon I0 times the partial derivative with respect to lambda of Bn lambda at lambda equal to 0, and that on the right hand side is given by h prime nn prime delta I n prime summed over n prime, so that's just h prime ni. Of course, all this is true if you assume that you can drop this, that is, you are assuming that this is finite. Now notice that if I put in n equal to I in this expression, this drops out and you have h prime ii equals h prime ii, which is an identity. Or you could go back and instead of using the Feynman-Hellman theorem result here, you have just said that this is how, starting from the Schrodinger equation itself, you can actually get that the first derivative of epsilon I, which is lambda, at lambda equal to 0 is given by h prime ii. As I said, you don't really need the Feynman-Hellman theorem. It just makes some calculations slightly simpler. But what is interesting here is what happens when n is not equal to I. If n is not equal to I, this term drops out and you are left with del Bn lambda at lambda equal to 0 is given by this quantity h prime ni, this matrix element divided by epsilon I0 minus epsilon N0. This should not come as something which is new, because anybody who has done perturbation theory would know this is the wave function correction from first order in perturbation theory. So, what perturbation theory tells us is the correction to the first order wave function, the nth component of that. Our Schrodinger equation, by doing a direct derivative, yields us exactly the same result. Of course, all this is correct provided the sum h prime ni del Bn prime del lambda at lambda equal to 0 is finite, and because we now know del Bn del lambda equal to 0 has to be given by this, what we are demanding is this quantity is finite. Now, this finiteness is actually related to the second order correction in the wave function, something we are going to soon see. It's not exactly the second order correction to the wave function, but if the second order correction to the wave function is finite, this quantity will also be finite. So basically what we have found out is the following. If the second order correction to the wave function according to perturbation theory exists, that is, it does not diverge, then the first order correction to both the energy and the wave function as predicted by perturbation theory exactly matches the first order derivatives of the functions epsilon I lambda and Bn lambda. Of course, we must remember one thing. We have found the first order derivatives of Bn lambda with respect to lambda for all n except for 1. The wave function which is actually being perturbed, the ith, del lambda cannot be derived out of this expression. Of course, that's a great thing because this expression actually gives you an infinity if you put n equal to I. But this formula, remember, is valid only when n is not equal to I. But we can easily figure out what Bi lambda is going to be or what its derivative is going to be just by using the fact that the wave function is normalized. Bi mod square is 1 minus sum over all the Bn mod squares. So, if you just differentiate this, you get Bi star del lambda plus Bi del Bi star del lambda is negative of this sum for n not equal to I. Now at lambda equal to 0, the right hand side will vanish. I don't even have to do this calculation here to see it will vanish, because when lambda equal to 0, this becomes delta in, this becomes delta in star, which is also delta in, and because n is not equal to I, the delta ins will all vanish, so you will get a 0. So the right hand side definitely vanishes as lambda goes to 0. The left hand side actually tells us at the same limit that this is 1, so is this. So del bi del lambda plus its complex conjugate is 0. So del bi del lambda and its conjugate, both of them, are purely imaginary. Now if you choose bi to be real, which can always do by absorbing an overall coefficient, what this says is bi, the wave function coefficient for the ith wave function, that does not change, at least in the first order. Del bi del lambda, lambda equal to 0 is 0. So as far as the wave function coefficients are concerned, we have two equations. When n is not equal to I, we have this familiar first order perturbation theory result, which here has been derived without invoking perturbation theory, has been derived directly from the Schrodinger equation itself. And del bi del lambda, that is the case for n equal to I, is simply 0. Let us now carry out a similar analysis with the Feynman-Hellman theorem, which in terms of our functions is written in this form. We have already seen that this directly gives us the first derivative of epsilon I. But now we are going to try to use it to find the second derivative. And the route to that is obvious. We just differentiate both sides of this equation with respect to lambda. And that gives us this. On the left hand side, you have del 2 epsilon I del lambda 2. On the right hand side, the h prime and n prime is an overall factor. It stays out of this derivative, of course not of the sum. And inside the bracket, you have a derivative of this product. Now what we need to do is put lambda equal to 0. Notice that the sum over n and n prime runs over all values of n, including I, but for n equal to I, this term is simply 0. So is this for n prime equal to I. So what we are going to do is sum over n and n prime. In this term, this is going to be for n not equal to I, and in this term, it's going to be for n prime not equal to I. The corresponding terms for n equal to I and n prime equal to I are actually just 0. Instead of bn prime and bn star lambda, we just put in the delta symbols, and you have this h prime and n prime on the right. So this simply becomes n not equal to I sum. If you just look at this, h prime ni's conjugate is h prime in, the standard result from quantum mechanics. Delta in prime, h prime, n prime, summed over n prime. So here I have carried out the sum over n prime. Will simply give you h prime ni, this term, and of course this denominator. And because the sum is over n not equal to I, this denominator does not cause a problem. In the second term, I'm going to use delta in to sum up over n first. So this h prime will become h prime I n prime. And this is of course h n prime I as written, and this is also a sum over n prime not equal to I, which protects us from this denominator here. But it's easy to see that both of these are exactly the same, with just the dummy index changing from n to n prime. So it's double of any one of these. So 1/2 of the second derivative of epsilon I with respect to lambda at lambda equal to 0, which is nothing but the second term in the perturbation expansion, the coefficient of lambda square in the perturbation expansion, is actually given by this expression, which should be again very familiar to anybody who has done a course in perturbation theory. This is the second order energy correction which perturbation theory predicts. So what we have figured out here is what perturbation theory predicts to be the second order energy correction is exactly what our second derivative of epsilon I also tells us. So just like the case for the differential equation that we handled in the last lecture, the derivatives are giving back the same coefficients that the power series method gave us. So although there the power series method was a bit suspect mathematically, the result it gave was correct. Here we are taking the same approach. These perturbation theory coefficients are the actual derivatives, apart from the p factorial term, from direct differentiation. So far we have got the energy correction to two orders and the wave function correction to one order. To get the second order wave function correction, we start with the Schrodinger equation once again, or rather we start with what we have obtained by differentiating the Schrodinger equation once with respect to lambda. This is the equation that we had used there. You partially differentiate this with respect to lambda once again. You get del 2 epsilon I del lambda 2 times bn lambda from here. A single del epsilon I del lambda del bn lambda del lambda from this, but you also get another such term by differentiating this factor with respect to lambda. So this comes with a factor of 2 plus this factor into the derivative of this here. On the right hand side, you get h prime nn prime del bn prime del lambda from this. Also a similar term again from this when you differentiate just lambda. And a final term which has a lambda in it, which is h nn prime del 2 bn prime del lambda. By now, of course, you know the drill. You are going to put lambda equal to 0 in this expression. So using the results that we have already obtained, this is going to be del 2 epsilon I del lambda 2 at lambda equal to 0, which we already know by the way, using the Feynman-Hellman theorem, times delta In. This is twice h prime II, first derivative at lambda equal to 0, first order perturbation theory result, times del bn del lambda at lambda equal to 0, a result which we had actually calculated already, plus this energy difference into the second derivative at lambda equal to 0, times this expression twice sum over n prime h prime nn prime del bn prime del lambda equal to 0, again something we already know, plus another term which is 0 times this whole thing and which we are going to drop, assuming of course that this stays finite. If you drop this, for n equal to I, not 1, it's easy to see that this is actually going to give me back the second derivative del 2 epsilon I del lambda 2. As I've said, you don't really need the Feynman-Hellman theorem. It just makes calculation a bit easier. But you get exactly the same result using that. For n not equal to I, of course, this term will drop out. And assuming that this sum is finite, this will also drop out. So you are left with this result. Twice h prime II times del bn del lambda at lambda equal to 0, which is h prime ni by the energy denominator, plus this energy term into del 2 bn del lambda at lambda equal to 0. On the right hand side, you get twice this sum h prime nn prime. This is h prime n prime I by epsilon I 0 minus epsilon n prime 0. Again, a result which we had already figured out before. And this tells us that provided that this sum can be dropped, or rather this sum is finite, so that 0 times that can be dropped, you end up with this second derivative of bn with respect to lambda at half of that actually, at lambda equal to 0, which is the same thing as the coefficient that you have at the second order in the expansion of the second order wave function with respect to phi n. You work it out to be simply this. It's just what you get when you take this and remove everything else to the other side. So this term divided by epsilon I 0 minus epsilon 0, which can go inside the sum simply because the sum is over n prime, and another term which comes from this where you have a square in the denominator. This again should be familiar as the second order correction to the wave function. Of course, now that we have obtained del 2b and del lambda 2, we can plug that back here and see that in order that these calculations be right, this sum should be finite. And this result is actually related to the third order wave function correction. So as long as the wave function correction to the third order exists, as long as it's finite, then what we have found out is up to second order in perturbation theory, whatever coefficients we find out using perturbation theory are exactly the coefficients that you would get by directly differentiating the Schrodinger equation. We could of course keep on going to higher and higher orders, but it's pretty easy to see what the pattern is going to be like. And we could think of differentiating the Schrodinger equation here with respect to lambda p times. And that will give us this factor times del b and lambda del p plus p times del epsilon I del lambda p minus 1, p into p minus 1 by 2 factorial del second derivative, and so on. All the way up to the pth derivative here on this side. Since we do not know what kind of function epsilon I lambda is of lambda, I do not know whether any of these derivatives vanish, so I have to keep all of them. On this side, you get one term which comes out by differentiating this and leaving this intact, so lambda times this derivative, plus another term which comes from p times differentiating this and differentiating this p minus 1 times. So finally, if you put lambda going to 0, what you get is epsilon I0 minus epsilon N0, p factorial times this coefficient of the perturbation series, plus p times epsilon I1, p minus 1 factorial, the coefficient of the perturbation series for the wave function at the p minus 1 order, similar term here, and so on. And on the right hand side, you will get p times hn prime p minus 1 factorial cn prime I p minus 1. The p minus 1 factorial simply is because the coefficients are the derivatives at lambda equal to 0 divided by the corresponding factorial. So the p minus 1 derivative divided by p minus 1 factorial was this coefficient. Now notice that these factorials here actually cancel out on both sides. Here you have p into p minus 1 factorial, which is exactly p factorial. Here you have a p from the Leibniz rule, and you have a p minus 1 factorial coming from this derivative. Here you have p into p minus 1 by 2 factorial, a 2 factorial coming from epsilon I2, because you have the second derivative here, which is actually 2 factorial times epsilon I2. And a p minus 2 factorial coming from the p minus 2 derivative of bn. So, p minus 2 factorial into p minus 1 is exactly the p factorial, which we are cancelling on this side. So, all the p factorial terms cancel and you are left with this formula. Epsilon I0 minus epsilon N0 into the wave function correction coefficient plus j equal to I to p sum of epsilon ij. The j equal to 0 term is actually here, and cn I p minus j. So you have j here, p minus j here. And on this side you simply have hn prime, cn prime, I p minus 1. I will leave this as an exercise for you to show that this is exactly the equation that you would get in the pth order of perturbation theory. And here, if you just use I equal to n, you can actually get the nth energy correction. And if you just use I not equal to n, you will get the wave function correction. The point is, by directly differentiating the Schrodinger equation, the equation that you have obtained is exactly the same equation that perturbation coefficients obey. So, the only catch in this whole problem is this term that we dropped has to go to 0 when lambda goes to 0. That is, this term has to be finite. This term, of course, is related to the pth wave function correction. This has to be finite. And from the formula that we had obtained, which actually had Cn prime Ip minus 1 here, we can figure out what this term that we are dropping or that we are considering to be finite really is. All you have to do is change P to P plus 1 everywhere here. And you get this. And in this, if you have got all the coefficients correctly by perturbation theory, or if you have actually obtained the coefficients as finite coefficients up to pth order, then everything on the right hand side exists, and this is just a simple sum, except possibly one term, which is Cin P plus 1. This P plus 1 is derivative. So, for our result, for the perturbation theoretic results to match the derivatives, the wave function correction of the next order, the Cn I by P plus 1, must also exist. So as long as the perturbation theory coefficients exist, what we have proven is they correctly reproduce all the derivatives of epsilon I lambda and Bn lambda at lambda equal to 0, which essentially means that the perturbation series which we get by using those coefficients are nothing but the Taylor series expansions of epsilon I lambda and Bn lambda. So, it doesn't matter whether they converge or not. These series are going to be asymptotic to the actual functions. This is one major lesson that we had learned in the last lecture, that if a function has all derivatives at x equal to x0, here lambda equal to 0, then the Taylor series expansion about x equal to x0, irrespective of whether it converges or not, is asymptotic to that function as x goes to x0. So if all the coefficients in the perturbation series exist, then the perturbation series are always asymptotic to the actual physical quantities that you want to calculate. Also, as we have already discussed in the last lecture and recapitulated at the beginning of this one, these derivatives existing actually tell you that the perturbation series is unique. So unless coefficients in a perturbation series diverge themselves, the perturbation series that you get is unique and it definitely is asymptotic to the results. Of course, if you're dealing with something like quantum field theory, then the perturbation expansion might even diverge in a very different way. Then even individual terms in the perturbation series may diverge. That has to be handled by using special techniques called renormalization, something we are not going to cover here at all. Our worry was with the standard perturbation theory in quantum mechanics, which leads to a series which may or may not converge. Does not converge more often than not. But what we have established is as long as all the perturbation coefficients are finite, the series that we have obtained exactly reproduces the derivatives of the corresponding functions. So that series is actually asymptotic to the corresponding functions. Okay, so now we are in a position to believe that the perturbation series, even if it diverges, is at least asymptotic to the actual physical quantities that we want to calculate. But what consolation is that to any of us? If the series actually diverges, can we use it to really figure out some results? We had seen in the last part of this lecture, the part 1 which dealt with asymptotics, that sometimes asymptotic series actually makes it possible for us to extract numerical values with less difficulty than slowly converging series. The asymptotic series actually can help us to find numbers. Let me just justify the same thing in this context as far as the perturbation theory is concerned. I will focus on the energy coefficients here simply because energy is the thing that we actually calculate more often. However, the same argument can also work for the work function corrections. So, let's put it this way. Say the P plus 1th coefficient in the perturbation series for the energy of the ith level, epsilon I P plus 1 is positive. Then the perturbation series summed up to P terms underestimates epsilon I lambda for sufficiently small but positive lambda. It's not necessarily true that it's going to underestimate epsilon I lambda for all lambda, but there will be some sufficiently small lambda for which this will provide an underestimate. We will see why that is important soon, but first let us prove that this is true. The proof actually is pretty straightforward. We have already established that these coefficients epsilon ij's are nothing but the partial derivatives, the jth partial derivatives up to a factor of 1 by j factorial at lambda equal to 0. So the perturbation series summed up to p terms, sum over j from 0 to p of epsilon ij lambda to the j is nothing but sum from 0 to p of 1 over j factorial del j epsilon I del lambda j at lambda equal to 0 multiplied by lambda to the j. And hence this is nothing but the Taylor series up to lambda to the p. And that is a finite Taylor series. So this much is a finite Taylor series for epsilon I lambda. And we know from the basic theory of Taylor series that epsilon I lambda is given by this plus a remainder term. And the remainder term is lambda to the p plus 1 by p plus 1 factorial times the p plus 1th derivative of epsilon I evaluated at some point theta lambda between the center lambda equal to 0 and the value lambda. That is, theta lambda is somewhere between 0 and lambda. So theta is somewhere between 0 and 1. Now we have already assumed that epsilon I p plus 1, the p plus 1 term in the perturbation series, is positive. This is the value of this derivative up to a factor of 1 over p plus 1 factorial at lambda equal to 0. Now if this quantity is positive and assuming that the perturbation theoretic coefficients are continuous, what we automatically get is there must be a range of lambda for which the derivative del p plus 1 epsilon I del lambda p plus 1 is positive even when lambda is not equal to 0. So there is a range from 0 to lambda for sufficiently small lambda where this derivative will be positive. As a result, epsilon I lambda, the actual value of epsilon I at lambda, will be given by the Taylor series up to p terms, p plus 1 terms actually, but we should rather say it's up to lambda to the p, plus this correction term which is positive. So the perturbation series to p terms actually underestimates epsilon I lambda. So that's a very important result. Now why is this important? Before we get to that, we also need to see that very similarly, if epsilon I p plus 1 were negative, then the sum of the first p terms of the perturbation series actually overestimates epsilon I lambda rather than underestimates it, at least for small enough lambda. This again essentially is because the remainder term in this case is guaranteed to be negative at least for small enough values of lambda. Now, using these two results, what we can easily see is the following. If two terms in the perturbation series, two successive terms, epsilon I p plus 1 and epsilon I p plus 2, have the same sign, then the sum to p plus 1 terms is an underestimate or an overestimate. Let's assume that both of these have the same sign, that is, both of them are positive. Then the sum to p plus 1 terms is an underestimate. So is the sum to p terms. But the sum to p plus 1 terms is larger than the sum to p terms because a positive term has been added. As a result, the sum to p plus 1 terms is closer to epsilon I lambda. Both are underestimates, but this one is larger, so it has to be closer to epsilon I lambda than the sum to p terms. So adding one more term to the perturbation series improves the approximation in this case. Now, if both of them were negative, the same argument would work. There, both of the results are overestimates, but the sum to p plus 1 terms, which has one more negative term added to it, is smaller. Both are overestimates. The smaller one, which is the sum to p plus 1 terms, must be a better approximation. So this way at least we can judge how we are improving on the approximation. Equally importantly, if epsilon I p plus 1 and epsilon I p plus 2, two successive coefficients in the perturbation series, had opposite signs, then the sums to the pth term, the one term before this, and the p plus 1th term would actually sandwich the actual value of epsilon I. If epsilon I p plus 1 were positive and this one were negative, then the sum to p terms would be an underestimate and the sum to p plus 1 terms would be an overestimate based on what we have just discussed before, thus sandwiching the actual value in between. And if epsilon I p plus 1 were negative and epsilon I p plus 2 were positive, then the sum to p terms would be an overestimate, the sum to p plus 1 terms would be an underestimate, again sandwiching the actual value. So, using the coefficients of the perturbation series, we can figure out whether we are approaching epsilon I lambda, and sometimes we can bracket the epsilon I lambda between pretty tight intervals. Of course, if those results are not sufficiently accurate for your purposes, you can always appeal to other techniques like convergence accelerating transforms used on the divergent series that you have here. And as I have already mentioned in the last lecture, very often standard convergence accelerating transforms work better on divergent series than on slowly convergent series. So despite not converging, perturbation series from quantum mechanics actually can give us a lot of information and be of great practical use when we are trying to figure out properties, especially for small values of lambda. Indeed, there are ways in which divergences of these series can even lead to results of non-perturbative nature being obtained from them. This is a quite advanced mathematical topic and I am not in a position to really discuss this. But at least let me state that a lot of research is going on at present in making use of the perturbation series in other ways than to just use them to directly calculate certain values. Many other important features can also be extracted from the series, and this is still a matter of active research interest. And so development of perturbation techniques is still a matter of active research interest. I hope this has actually given you some insight as to why perturbation series, despite the limitations, despite being divergent, can be quite useful things.